The PDB Reader is a required module whenever your builder workflow involves a protein structure. It provides the essential first step for preparing a protein or protein ligand complex prior to system construction. In this demo, we introduce the advanced options of the PDB Reader. Since there are 14 options in total, which can be difficult to explain all at once, we will instead present examples to illustrate each option in detail. We have already demonstrated the basic usage of the PDB Reader in a previous session. Here we will begin from step 3 to highlight the advanced options. If you need instructions on the basic functions, please refer to the earlier demo first. In this case, we will load the 3PQRPDB, which contains Metarhodopsin II, a photoactivated state of bovine rhodopsin, in complex with a C-terminal peptide fragment derived from the G-alpha subunit of transducin. In this dataset, chain A corresponds to rhodopsin, Metarhodopsin II, and chain B corresponds to the G-alpha-derived peptide ligand. After loading the PDB, the blue highlighted options are automatically activated. By default, 4 options are enabled, and we will additionally enable the mutation option manually. 1. Chain selection. In this case, we will load the 3PQRPDB, which contains Metarhodopsin II, the photoactivated state of bovine rhodopsin, in complex with a peptide fragment derived from the G-alpha subunit of transducin. The structure also includes standalone ligands such as SO4, sulfate ion, and ACT, acetate, glycan chains, GLYCA, B, C, D, E, and optional water chains, but these ligands and waters will not be selected for analysis. 2. Model missing residues. The PDB Reader can automatically generate missing residues in each protein, and most options are suitable by default. However, note that modeling more than 10 consecutive missing residues may result in an inaccurate structure. In this PDB, the missing residues 327 to 348 are located at the C-terminal region, and it could generate an inaccurate structure. You can keep the default selection. 3. Disulfide bond. If your PDB contains disulfide bond information, it will be listed here. In this PDB, a disulfide bond is present between cysteine 110 and cysteine 187 in chain A. The bond is automatically detected and included by default, and you can choose to keep or delete it as needed. 4. Glycosylation. If your PDB includes glycan modifications, they will be listed here. Each glycan chain is associated with its glycan sequence and type and can be edited or deleted as needed. In this PDB, multiple glycans are present. Glyc-B, C-E are listed as ligands with simple glycan sequences. Glyc-A is an N-glycan linked to Prot-A at residue 15, with a complex glycan sequence including mannose and N-acetylglucosamine units. Glyc-D is an N-glycan linked to Prot-A at residue 2. Any glycan chains will be displayed in this section. You can also add a new glycan chain or further customize the existing chains using the glycan modeler, including adjusting the number of sugar units. Unsupported modifications will be automatically removed and reset as modified glycan chains. 5. Covalent ligands. Any covalent ligands in your PDB will be displayed in this section. You must select how to generate their force fields. Several force fields are supported with OpenFF, fast selected by default. The PDB Reader automatically creates covalent ligand structures based on their SDF structures, but you still need to carefully check and validate their geometry. In the drawing modal, atoms highlighted in gray cannot be modified. The automatically generated ligand structures can be confirmed and applied by clicking the Validate Structure button, which ensures that the geometry is consistent and avoids potential collisions. In this PDB, 2 covalent ligands are identified: LRET, linked to Prot, a residue 296, lysine, CPLM linked to Prot, a residue 323, cysteine. Additional options allow you to create a covalent ligand or create a conjugated ligand, while the Reset button clears the current setup. 6. Terminal cappings. In this option, terminal capping is applied by default. If you want to generate a cyclic peptide or protein, you must select cyclization. In this case, however, you may choose neutral caps, charged caps, or apply custom caps depending on your modeling needs or the force field requirements. Here, we will keep the default selection. After setting all the options and clicking Submit, the generation begins. This process takes some time. Once the generation is complete, PDB is properly loaded, and that glycosylation can be appropriately inspected. The resulting PDB can then be used for various studies such as MD simulations or free energy calculations.